This project centers around a critically important real-world problem in the field of radiology and medical imaging, the detection of cervical spine fractures. Your cervical spine are the first 7 vertebrae from your head and are especially sensitive, with injuries often leading to paralysis or death if not identified right away. There are over 1.5 million cervical spine fractures each year in the United States alone, a large portion of which are from elderly people. This is problematic because degenerative diseases like osteoporosis, which are common in elderly people, make detecting fractures dramatically more difficult. This project presents a number of real-world challenges that go beyond just training a model. We had to look at this from the perspective of its real-world application, where missing a fracture, a false negative, could be fatal. That meant prioritizing sensitivity, or the ability to catch all true fractures, even if it meant occasionally flagging healthy vertebrae. Balancing this with model performance was a struggle, and it all started with understanding the data.
For our training data, we have 2019 CT scans. We have segmentation data for 87 scans and bounding boxes, which show the locations of fractures for 240 scans. Each scan is broken down into hundreds of DICOM files, where each DICOM image is a horizontal slice of the scan, starting at the head and moving downward through the body. DICOM files contain data in the form of Hounsfield units, which represent the relative density of bone and other materials in the body. The values use water as a reference point, so water has a value of 0 HU. This is a single DICOM slice from a scan. The denser tissues, like bone, appear brighter because they absorb more X-rays. Our Nifty files contain our segmentation data. They have hundreds of layers, and each layer is a mask which corresponds to a single DICOM slice. Each mask is basically a matrix of numbers where a pixel is given a value from 0 through 19. 1 through 7 corresponds to the cervical vertebrae, 8 through 12 corresponds to the thoracic vertebrae, and then everything else is just labeled as a 0 for the background.
In our first approach, we used YOLO to try to find the location of fracture. In order to use YOLO, we needed to create a script that writes to a CSV to congregate all of our important data together. This CSV contained rows that had the study IDs that had bounding box coordinates, as well as the coordinates themselves, and the slice number they could be found in the DICOM files. After setting up the CSV and creating proper variables for the file paths, we began creating the files needed for YOLO. This is where we ran into an issue. We didn't include any study IDs in the CSV that had unbroken vertebrae, so all of the labels and images we would have given to YOLO would have been broken vertebrae. For accurate results, we need to give YOLO unbroken vertebrae as well. To fix this, we altered the script that generates the CSV to find an equal amount of unbroken vertebrae images to our broken vertebrae images. With this fix, YOLO is being trained on a 50-50 split of broken and unbroken vertebrae images. After we had made a proper CSV containing all the data we need, we created the file structure required for YOLO to work. We then converted our raw DICOM images into JPEG without any pre-processing. If the image showed a broken vertebrae and had a bounding box, we created a label file stating that this was a broken vertebrae image and provided the coordinates. However, if the vertebrae was unbroken, we created an empty label file so YOLO would classify it as background. At this point, we realized we made another critical error. We did a train test split on the DICOM slices themselves and not on the study IDs. This gave us unrealistic accuracy due to bias. The accuracy was so high because adjacent slices are very similar to each other, and we were essentially training and testing on these adjacent slices. To fix this, we did a train test split on the study IDs themselves and moved through the rest of the pipeline as normal. To summarize our first run of YOLO, we've converted raw DICOM images to JPEG. We experimented with changing the parameters in YOLO models like the YOLO 8 small and the YOLO 8 medium. Our results were not desirable. More on the results later. It was clear we had to go back and fix some things. For our second run of YOLO, instead of converting raw DICOM straight to JPEG, we pre-processed the DICOM images. We thresholded them, finding the range of HU units that was best. This was around 200 to 1500. We performed histogram equalization to try to maintain as much of the important data as possible after conversion. Using these images, we attempted training again. For our final run of YOLO, we combined Michael's mask segmentation prediction model into our YOLO pipeline. This meant that we were training on the pre-processed images as before, but only the regions inside the predicted masks Michael's model generated. We had another oversight here, where we didn't generate masks for the unbroken vertebrae images and only for the broken.
My segmentation model is a UNet model, so in the first half, features are extracted, and then in the second half, the mask is upscaled to fit the original input size. I had originally used Keras and TensorFlow for a UNet model, but long story short, there were memory issues and we were having on the server, and I ended up remaking my entire notebook using Torch and PyTorch resources, and the model was able to run even with the server issues. So I ended up sticking with PyTorch and using transfer learning with the pre-trained model, ResNet 34. And the best IOU for the test dataset ended up being about 70%. During its best performance, the model was predicting high-intensity vertebrae well, and it was also ignoring non-cervical vertebrae. I attempted a histogram equalization for detecting low-intensity vertebrae, and it did seem to help in some cases, but it brought my overall accuracy and IOU scores down because I was just equalizing all the images, and I think that actually made it harder to detect vertebrae in other cases because it was actually lowering the intensity for those vertebrae. Something else I noticed is that there are misaligned ground truth masks, and I'm not sure if this was intentional from Kaggle, but even if my model looks to be correctly detecting the vertebrae, cases like this lower its performance. For anybody taking on this project, some of the things I would recommend are also things that I didn't have time to implement myself, but the first thing I would personally recommend would be to use Torch resources and transfer learning. It will help you get started a lot faster. I would try different input sizes for the segmentations to see if that would help at all, perhaps even keeping the original input size. Look through the data and try to fix or remove the misaligned ground truth masks. I would first perform a check before doing histogram equalization to make sure you're only applying it to images that actually need it. I used the dice loss function, but I would also test different loss functions used for segmentation models like Jacquard. For my fracture detection model, I used a faster RCNN model, which basically just proposes regions for the image and performs feature extraction on those regions, and then uses that information to try to classify any objects. I did a lot of data pre-processing before using the data in the model, and this is what a single sample looks like. So in this case, the input for the model will be this portion of a DICOM image, which has been segmented out using a dilated mask. And the output will be a label of 1 for a fracture and a bounding box. In this case, the green bounding box, which shows the ground truth.
I will now go over our results. Here are the results for our first model. From our confusion matrix, we correctly predicted 680 fractures, which are our true positives, and correctly identified 1,182 non-fractures, which are our true negatives. However, we mistakenly predicted 189 unbroken vertebrae as broken, which is false positive, and more importantly, we missed 895 actual fractures, labeling them as unbroken, which is considered false negative. Some important terms we need to remember are precision and recall. So, precision is asking, out of all the times the model predicted a fracture, how many were actually correct? Recall is saying, out of all the real fractures, how many did the model find? We had a confidence score of 20%, meaning the model needs to be at least 20% confident that a region contains a fracture to report it. In spine fracture detection, our primary focus should be on achieving high recall, even if it means sacrificing some precision. This is because the consequences of missing a fracture are far more severe than an inconvenience of a false alarm by mistakenly identifying a non-fracture as a fracture. Failing to identify fracture can lead to permanent damage or even death. While a false positive might lead to an unnecessary follow-up scan, a false negative can be life-threatening. For example, precision was 29% in epoch 17 out of 100 epochs, but the recall in the same epoch was 23%. Since this is still low, we must keep focusing on recall in this context, making sure we identify as many true fractures as possible. With the combined methods, our model performance is once again low. We use a 20% confidence threshold. From the confusion matrix, we correctly predicted 417 fractures and correctly identified 1,714 non-fractures. We had 0 false positive, meaning our model did not mistakenly classify any healthy vertebrae as fractured, but we missed 990 actual fractures, which means these fractures were incorrectly labeled as unbroken. For this model, our precision and recall were slightly higher, with the highest precision being 31% and the highest accuracy being 26%. This slight improvement is promising, but the high number of false negatives suggests that our model is still struggling to consistently identify fractures, which remains a critical concern. The precision recall curve helps us understand how well our model balances precision and recall. Our MAP 50 score is 0.188, which suggests that the model is struggling to accurately detect fractures as it's not consistently identifying them even with an IOU threshold of 0.5. This low score indicates that our model may be having trouble learning features that can distinguish fractures from the healthy vertebrae. To improve this, future steps could include experimenting with different hyperparameter settings or exploring alternative models to better capture the small but critical details needed for accurate spine fracture detection. Here is an image of the validation batch showing our ground truth on the left and the predicted results with a confidence threshold of 20%. As you can see, while our model was able to correctly identify some fractures, it also missed others, showing that we need for further improvement in our detection approach. So, what have we learned? Over these weeks, we faced significant challenges in understanding the complexity of our data, but we made meaningful progress. We gained experience with new data formats like NIfTY and DICOM, which were initially unfamiliar to us. This project also deepened our understanding of YOLO and other model architectures, showing us the importance of data processing and model selection. Beyond just the technical skills, we strengthened our abilities to work as a team, clearly communicate ideas, and effectively assign tasks to meet deadlines. These skills will be important as we work on future projects. For the next team, we recommend to take the time to fully understand the data before diving into the modeling. We spent a lot of time figuring out the cervical spine fracture dataset and how it was structured, including differences between NIfTY, DICOM, and CSV files. One key lesson we learned late in the process was that our final dataset included both fractured and unfractured vertebrae, but only the fractured one had mask. This likely impacted our model performance once again. We recommend creating masks for the unfractured vertebrae to create a more balanced dataset and to improve model and performance. Our notebook also includes detailed comments and markdown cells to help you guide you through our approach and avoid the same mistakes that we did. Thank you and good luck.
These are the results for the mask segmentation model.
This model is not performing well at all. The classification report and the confusion matrix basically just shows that the model isn't really learning anything. It's just guessing when it classifies, which is why there's almost a perfect 50-50 split. And I think the reason why it even learned to do this 50-50 split is because I trained the model on data that was half fractured and half no fracture data. The IOU score shows that it really hasn't learned to predict bounding boxes either. Even if it guesses correctly that there is a fracture, it is not even producing a bounding box at all, as shown by these predictions here. What I would do if I had more time and what I would recommend for future students would be to try using the original input sizes. I downsized I downsized my image to 256, and so the predicted masks are also 256, and so I'm not sure if I lost information by doing that. I would also try to zoom in on the vertebrae after masking them so that the model has more to focus on rather than excess background. I would also split the datasets differently so that there is a majority of fractured images. Right now it's 50-50, and I would see if that would help. But I would also just recommend using an RNN model instead, since it's designed to process and predict sequential data, which is exactly what we have.